Yo, yo, yo. Hello, everybody. Welcome back to another episode of this series. We're still trying to write our kernel from scratch. Last time we've started thinking about the descriptors, GDT, IDT, and all the task segment descriptors. And I think I was a bit ambitious talking about the task state and stuff like that this early on. We surely are going to see this again when we do scheduling. So I'm taking the executive decision to basically just Men in Black style flash you guys and just act as if this never happened. Right. So here how I want this to go. Instead of having GDT here that takes a base, the way I want to make this is, since I already know how many entries I want in my GDT, I am just going to pass that number as a const or comp time const, I guess. We could say that. Actually, if we could construct this struct here at comp time, if we could, for example, just store these descriptors that we want to add. Actually, this never exists. This never happened. If we could store these descriptors and we could just create a GDT and have it at comp time, create the descriptors and store them and compute the length, that would be great. But I'm not sure there's a simple way to go about that. So I'm just going to do the easy thing for now. So const GDT or function GDT goes takes a comp time. I guess we could use a comp time int. So I guess let's call this num entries. Should take this as a comp time int, and it would return a type. And the type it's going to return is this minus the name. Right, so this one here should not do anything, I think. That's fine. Right, so here we go. So we want this to allocate a page. So we'll have to look into that. And this will actually have a, I guess we could just use num entries to compute the size of what we want to allocate. Yeah, actually, should be fine. So let's go to memory here. So I think we are going to need to allocate one page, and yeah, we did not fix this. This is going to be fun. Right, and then we are going to need to map said page to a virtual address. And do we have like allocate here? Let's see. We have allocate range that basically just allocates from the virtual memory range. It's not doesn't have any physical memory behind it, and yeah, very nice. So very cool. Right, so let's make this happen, I guess. This here would take, so if I go to main, and here we got a VMM by initializing this. I think this is kind of bad because we would like this to be used from elsewhere. And so the initialization should, in theory, just set this as a global variable somewhere. Yeah. Or we can just, for now, say that we take that as an argument, kind of like an allocator. So pmem, which would be, what was the type of that thing? No, not this one, this one. This one returns a physical memory manager. Nice. So this one is a physical memory manager. And we are going to have to get that physical memory manager import from so memory pmem. Yeah. And I think we need to do pretty much the same thing. So virtual memory manager from so memory vmem. It's like, yeah, cool. So now here we go. We need a virtual physical memory manager. We need a virtual memory manager. This is not the final interface, by the way. We still need to work on our memory management stuff. Just did not get to that just yet. Right, so pmem.allocate page. And I guess we need to count how many pages we'd like. Actually, now that I think about this, can't we just take the heap allocator that we've just created? So heap allocator. Right, we haven't used it yet, but we could, in theory, just use a body allocator with a bunch of pages mounted onto it as memory. And we could use that to allocate, since it implements the allocator interface. Yeah, but we'll have the alignment problem because we have not handled that. All right, fine. Let's just go with the flow for now. So we need to compute number of pages. So const page count would be, I think there's something instead math. Was it instead mem align forward, align forward, and I think we should have this as a USI 64. The address we have is I guess that would be num entries times the actual size of the GDT. So hold on 1 second. So that would be 8 bytes times the number of entries plus the GDT header itself, which we haven't yet defined. But that should be fairly easy. So let's actually create it here. So GDT header, let's attach them, is struct, and this one is fairly simple. It just has a base, which is I think a U32, and it has a limit, which is a U16. Let me check. So if I go to start.asm, and it should be down here somewhere. So yeah, a word which is a U16 and a double which is a U32. And this one here has the size, so start minus and minus 1. Rather, and minus start plus 1. And here we align this to 16. But I think we did that as an arbitrary thing. Yeah. Yeah, I don't think we have any alignment requirements on those. We'll go through that right now, but we'll see. And this one would be an extern struct. Right. So this one would be name of num entries times the size of what did we call that? Descriptor 8 bytes. So descriptor 8 bytes plus rather, let me just put this in order. This would be size of what did we call this? GDT header plus num entries plus the size of thing. And the alignment is it should be constants dot page size. How do we call that? Arc page size. All right. And here we want page count. Or rather, wait a minute. We want this to be div exact of that size in bytes and constants arc page size. Yeah, that sounds okay. Right, so let's get constants is import constants .zeg. All right. Cool. So here, what do we have? What else do we have? We want to avoid to zero in this, so we'll set 0 to false. Let's say to true for now. Okay. Does this fail? I guess it does fail. So if how do we go about this? If this capture that as p page, yeah. Here we can go for else. And here we can return error dot no page, no fizz page. Sure, let's use this for our tests. Right, so what is the problem here? Oh, right, so this one is in segment. Cool. Right, and here we want to basically get the virtual memory from, or rather allocate or map our physical page to virtual memory. So we'll go for vmem dot so allocate range, and we want that range to be ppage dot length long. We don't really care about the type for now, so let's get the range. Can this fail? I think it cannot fail. So I guess const v range is that. Sure. And I guess we are missing some things in our thing here. We just cannot map pages. Whoops. Yeah, we're missing the most important function. So a map. This one here should take a physical address and a virtual. Right, let me just do this a bit more nicely. So now that we have our virtual range, if I can find virtual range. Yeah. So on virtual range, I think I'm going to define a function, a map, or rather I'll call it map to map physical. Yeah, sure. And this here would take a self, which should be a pointer to self, I think. And probably add mapped boolean false here, just to track if it's mapped currently or not. Or actually, I don't know how useful this would be. Yeah, sure. Let me just change this to map. And here we are going to take a physical range, I think. So P range, which should be physical memory, physical mem range. I don't know how it's called, but for now let's to do like this. Great again. Right. So phys mem range is at import so pmem I think .sig and inside that we should have okay. So where is it? So this one here should be made public, physmem range, and this one here should be physmem range. Yeah, sure, it's not great, but for now it's going to allow us to move forward, so I'll take it. Right, so here we get a physical, should be, so this physmem range. This one returns false or nothing, and we should do at the end of this, if it succeeds, we should not forget to do self.mapped is set to true. Yeah. Oh, we don't have self, so this. And p range is not used, of course. So here we check if self.length is larger or equal or rather smaller than p range.length. And I guess this can error. And here we return error dot too small. Sure. And then we should go and just do the mapping. Yeah. So then we could call into so we should have a function here which should not be public. Right, Right, let me just try some things here and see if there are any access issues. So where were we? We should be somewhere over here. Yeah. So can we do mmap? Yep, we can call it. That's fine. So we want to mmap the physical range. So p range dot start to self dot start dot yeah, sure. So let me just check if p_range.start is something. So it's just a U64. That's fine. Cool. Very nice. Right. So let's go and do that. This one here would take a self, which would be just the memory manager or virtual memory manager. And it would take, or rather, wait, hold on. We don't really need this, do we? Oh, we do. Shit. Okay. Fine. So this would need to take a pointer to add this. And then it should take a p start, which is a p address, and then a v address, which is a v address. Let me just change this to p address. And now we need to also get... so maybe I should do something like this and do pmem, sure. And that means that we are going to have to do pmem here, and that's fine, and here. Yeah. Okay, and here we are basically looking to do this, but by going through all the... actually, I think we already have this code somewhere in our EV5 bootloader. mmap. No, never mind. I think it should be in our C code somewhere. Did we not have vmm.c? So do we have mmap somewhere? Mmap to address. Oh, there we go. So we do have this code here. I could have sworn we have it also in address space. Yeah, we do have it. Nice. So it takes v address, p address, and some flags. Okay, well, happy with that. Let me just take that, go back to... we were here, I think, and put that there. And just going to return error dot something. Actually, no, we don't have these anymore. Yeah, okay. So this one goes, this one becomes this, like so, and this one goes. And this one also, this one goes, this one just becomes the address. Of course, something like this. And if we go to X and we replace it with P address, it should work. Yeah, and I guess here we should take flags as mmap flags. Cool. Okay. Very nice. So here we have get page entry? I don't think we do. So we need to get that. We have write entry though. That's fine. So address space get page entry, and that's all this. And I think we should also get our create mapping. Right, so if I put that here, that should not be public. And this should be just something like this. Yeah, we are going to need to allocate pages. Okay, well, here the plot thickens because we need to allocate pages, but we need to map the pages we allocate to write to them. Okay. This is becoming a different video, I think. Sure. So what's the problem here? Undeclared self. Yeah, okay. Oh, right. And here, this one becomes just a v address, and this one just goes. Okay. Right. So, we want to allocate a page, and I guess we are going to go through. We are going to need a pmem here, which is a physical memory manager, and that should be pmem.physical memory manager. Right, so here page. It's quite maybe page would be pmem. Okay, yeah, that's not a great name. That's not a great name, but sure. So pmem dot allocate. Okay, all right, hold on. Let's call this pm. Let's go here and call this pm, and we should go to anywhere that has pmem and change that to pm. Is that okay? No, there was another one here. This should be pm, I think, and this one should be okay. Right, so this one here is alloc. No. Is it alloc? No way. No, that's not it. Okay, so it's not physical memory manager then. So I think for our physical pages, we already have this set as a global variable here. We're just initializing that variable there, and we can use it from anywhere else. Okay, so that means that we don't really need this. And we can just go back to how things were. Okay, that's very nice. So I guess I could just remove that and do maybe page is pmem.allocate page. And here we just want one, and we want yeah, sure. Okay, and here if maybe page, and we take that as page pointer, sure, and we go something like this. And I guess we don't really need to do this anymore. Yeah, that's fine. And here we could do else and return a error. Let's call it physical allocation and error. Sure. Right, now that we have this page here, we should actually do a quick map on it. So hold on a minute. I guess we should have this also be in this object. So we can do self dot quick map. Oops. And quick maps takes a address as a U64, and I guess we could give it page pointer dot start. Yeah, that should do it. That should be fine. And of course, it gives us a const. How should we go this? So mapped is that. And here, of course, we get mapped. Although I'm not sure this needs to be that, since it's not a pointer anymore. The only problem here is that we are writing the address to next level. And the address we want to write is the actual physical address. But next level itself, the entry itself, should be allocated here. Huh. So where are we allocating this page? Okay, I see what the problem is. The problem is that we are assuming that this page already exists and that the so we don't really need to quick map this. We could just do that and go page pointer dot start here. Yeah, that means we don't need this. Okay, it's all fallen into place. And if we can't allocate, we return the error. Otherwise, we return a sure. So it's the new page becomes a collection of page mappings. That's fine, I think. So that should be okay, as far as I can tell. And now we can go here and do. So what should we do? Get page table entry with the virtual address, and we write the physical address to it with the flags. Okay, so that's seems pretty okay. So now we should go. So map. Okay, that's fine. Map. There we go. And this expects this, which should be the virtual memory manager. And the reason why we have this problem here is that we can have a virtual memory manager per page map, basically. We could have one for the kernel and one for the user space. So we actually are going to need a way to choose one. Right. I guess one easy way to go about this is to do I guess we can go for VMM. Sure. And this would be, well, actually it's not a VMM, it should be a VMem. and this would be at this, but not really this. It should be this thing here, which we haven't named. Okay, this is getting a bit complicated. Right, so how do we go about this? We can do something like vmem is at this. Sure, let's just define it that way. And let's see if this makes it any easier. Okay, cool. We'll have a bunch of things to change, but self-dot. At least this works here. And for now, let's just go for default mmap flags. Cool. And let's also do a public function unmap. For now, let's just have it as a sort of placeholder. This takes a pointer to, again, at this. And I guess that's pretty much all it does. So do we fail if we're not already mapped? So if not self.mapped, do we fail here? Do we return error not mapped? Sure. To do unmap the address. Actually, hold on. Let me see how bad that is. I guess it's fairly easy. Yeah, no need to do this. We just need to copy this, go down here, go for, so this one expects a P address. Let's go for 0x, 0x0, sure. And here for flags, we are just going to go present false. I think that's all it takes for it to be considered unmapped. Let me just go to default flags. So present is true, and yeah. So if we set as not present, then that means the page is not mapped. Yep. Okay, cool. So that's that. Now let's see if we have any other things that need to be taken care of. Well, obviously this needs to be tested, but sure. And we've allocated a range, and then now we are going to go for vrange.map, and we are going to map it to ppage, I think we've called that. And I guess map can fail, so we should try it. And it does not return anything, so that's fine. Okay, this was quite an excursion from what we tried to do, but all right. Okay, so page count, we set 0 to true, which we should probably not have done. It's already 0 by default, I think. And here we've set, we allocate a virtual range. This one does not fail. We mapped our physical range to our virtual range, and now we can use our virtual range to write to our physical range. All right, all this to say that now we can do something like const, let's just call it a for now, and do return Should we just return vRange? Yeah, sure. And let's do something like this. And of course, this one needs to be tried, I think. And so if I do a dot, why can't it, hold on. Is this not allowed? Is this not allowed though? I think it is allowed. Right, I think it's the return that's not allowed. We need to return from a block. Yeah. So block here, and here we should go ahead and give this a name block, something like so. Is this something we should do here? Maybe like so. Huh. Okay, not sure about this syntax for that. But okay, for now, let's just go with it. Let's see if we do set.log. Do we have a log here? No. Dot info and go for any, sure, and do something like this. So, okay. And this one would also go to that. This would go like so. Okay. I'm just going to try to build this, see if there are any problems. Yeah. So there are quite a few things that we've missed. So in vmem, I think that's 174. Okay, so here we are going to have a circular dependency, I think. Yeah. Yeah, we are going to have a circular dependency here. Okay, that's actually very bad. So we need to initialize the memory manager, in which we need to create the quick map entry here, except that the mmap entry itself needs to, well, it's is of type vmem range, which now needs to have so range, which itself needs to have a vmem and a mapped boolean for now. So yeah, this is actually impossible. Yeah, so we cannot use this way. This is unusable for now. So we are going to get rid of these, and I think we are going to need to use mmap directly the way it's set here. Okay, it's not too bad. It's not too bad. So we just need to get here. We just need to do vmem.mmap. Is this not? Oh, okay. I see what the problem is. Actually, this we can get rid of. pmem is well defined, I think. Well, this was wrong. And this is wrong too. So does this mean, so this one goes to vmem. Sure. And this one here, so VM should have a map, should be fine. Yeah, okay. So p address is p page dot start, and v address, do we not have v address? What did we call it? It's the, okay, so I guess it's just v range dot start. Sure. And flags would be so vmem dot default mmap flags. Sure. Speaking of which, should probably have yeah, I guess a map is just called an mmap with the appropriate flags. Yeah, for now I'm not too bothered about that. So does this one fail? It does not seem like it. I guess here we could actually take a pmem dot physical mem range and a virtual mem range. Sure. And just do the checks. Let's call this v range and this one p range. Sure. And we can do, for example, f so p range dot length is above v range dot length. Then we I guess return error dot too small. Sure. And this one here needs to be to return error. Otherwise, here we can do this dot start, and this one, of course, is p range, and virtual address is v range dot start, I think. Yeah. All right. That does simplify things a bit. So now we need to try this, except that now we can just basically go to just do this, which is a lot simpler. And I'm just going to rename this to p range. Sure. Okay. So now let's go back here, try to rebuild this. Okay. So if I do this dot start and I go here and do a try, does that work? Yeah, it does. Okay, that's cool. So I guess we can assume here that A is of type v range. So v vert mem range. vmem, of course, dot vert mem range. Cool. So we can get rid of that, and now we can. So what were we doing anyway? We were trying to create a GDT entry. We've allocated the page. We have it mapped to A. And actually, now that I'm thinking about this, we are also going to need the physical address for that. We are going to need the physical address because if we are going to load it here, the physical address is what we are going to load, not the virtual address. So How do we go about this? Let's, I guess, do var. Yeah, that's not really what I want to do. We can do much better. So what we are going to do is just split this to be pmem dot phase mem range, sure, and let's call this p range. And here we can do this and get rid of, actually, let me just do something like this, else return error dot phase allocation failed. Sure. Okay. Otherwise, this one returns p range. Of course, with that. And then this goes like so. This goes to be v range is. So I think we just need to do this. Call this a v range block. Sure. And this one would be return v range block v range. Is it break instead of return? I'm not sure about the syntax here. Or does this happen before? Okay. And I guess we don't really need this anymore. Okay. Since we are already trying this inside the block itself. Actually, what am I doing? I guess, oh, because this one, we're doing this because this one is returns a nullable an option value. Okay. That's okay, I guess. Right, so now that we have our physical memory and our virtual memory, we can go ahead and just use, I guess, the physical memory to write the values, and then use the use the virtual memory to write the values, and use the physical memory to create the struct. Since basically here we have not defined this, but we should have I guess we can just get rid of that. Just have this be here. I think that's not too far off what we want. And here we can just do load GDT of pointer to self, basically. Or rather just self, because it's already a pointer to self. Yeah, that's fine. So now we just need to set the base and limit. And to do that, we are going to just return so base, I think this one returns a pointer to self. Yeah, let's not do that. So base would go to be p range dot start. Some restrictions apply here. We need to make sure the start is in fits in AU32, and limit would be I guess we can extract this to be our const total size. I guess bytes is what we did here. Just get rid of this, and probably, oh yeah, we need this back here. So total size in bytes. Sure. and this should be the limit size in bytes. Right. So does this work? I think it does. Yeah, okay. That's not too bad. And I guess we can mark this as extern. Yeah, okay. Right, so now we want const. So let's think about this. So GDT entries, sure. And this would be a mini item pointer of segment descriptor 8 bytes. And this would be pointer from int, and the int itself would be int cast of p or rather v range dot start plus or rather plus goes somewhere here plus size of self. So basically skip the header and well then we need to return this as a pointer. Right, so return self, and here we need to create self. So const self, which is a pointer to self, and this would be I guess pointer from int, and the int would need to be int cast from vrange.start. Actually, yeah. So let me do something else here. Allocated bytes should be just a many item pointer of u8. U8 would be better, I think. And pointer from int of int cast of vrange.start. Sure. It's going to complain. I'm going to add as u64 to that. If we go here, it should be okay. So self here would need to be stud.mem.slice as, or rather no. Do we have bytes as slice? Bytes as value, actually. So the comp time here would be self, yes, and the bytes would need to be so allocated bytes from 0 to I guess size of self. Okay. What's the problem here? Okay, we need to close that. Actually, that's fine. At least it looks okay. And I think we can just get rid of this now. Should, I guess CLS is not really greatest at this, so let's leave it for now. Right, and this one here would need to be stud.mem.bytes as slice, I think. The slice is of type segment.descriptor 8 bytes, and the bytes are allocated bytes from size of self to basically the length of allocated bytes. Yeah. Okay. That's fairly okay. And I guess we can just have this as a slice. And we'll know the number of items in the slice. Cool. And this number of items, I think we can assert in the test somewhere that it should be equal to the number of entries we used to create them. Okay, very nice. So now we are going to just actually, I don't really know why I did this, since we're not going to need it. So for now, I'm just going to comment that out. Okay, so here we go. And I'm going to do something like this. So do I actually want to do this? Yeah, actually, I'm just going to skip. Yeah, I'm going to skip this for now. I'm just going to go back here, and I'm just going to go undo GDT entries. The first one would be I guess we can just create them. Or I can add, sure. Yeah, this would be useful, I think. So this one would need to be the same as this, except that everything else is a 0. Should I actually just put that here? What is type? Okay, so I guess we can create it. Sure, this one would be ring 0, I think. False. 0. I guess available is, it's not really a boolean, it's a U1. It's a bit we can set for ourselves, for our own use. Sure, we don't do anything special with it, so. And since we don't do anything special with it, I'm not sure I want it to be here. Yeah, that's fine too. So this one goes to that. This one is 0. So is this one. So is this one. And granularity, I think it's bytes. So I think I should just initialize this like so. So type is the only one I don't have. So let me just create this here. Sure. And that should actually be okay. And well, I guess that's just easy now. There we go. I'm just going to paste this 4 more times, I think. And have this here. And I think I'm going to need to create... yeah, so for these ones, I think I'm going to need to call create. And this one would need to have... so what should we be setting here? I think base. I'll set that to 0 for now. Limit, I think I'll just set to max. Should we probably do something like math max nth of U16? Yeah, so I'm not really happy with U16. I would have liked this to be something like function max value takes a some any type and figures out what the any type is, and if it's an int type, figure out the number of bytes and then returns the maximum for that int. Is what I would like to have, but yeah. So type is hold on. What is type? Type is so for type we are going to use one of the types we've already created. So kernel code type. Kernel code type. And I think this one here would need to be segment dot descriptor, or just segment, I think. Yeah, just segment. Right, so what else are we going to need? So these ones are the ones we need to set, and these two. So it's 64 bytes and size. And this one would need to be true, I think, and size would need to be... so I forgot what size needs to be, but I think I'm going to put a 1 in there for now. Okay, so let's get this and just paste it in here. And this one would be 4. Cool, so this one would be kernel code, this one would be kernel data, and I think we need to do something about the data thing. So this one is code, and this one is user data type. Right, so for the data type, I think we are going to need to add something more, which would be... oh no, it's actually already in the type. The write enable and stuff like that, it's already in the type. So that's all we need to do, I think, for now. And now we are going to need to see for the load. Oh, right. So here for LGDT, I think we are going to go for sure volatile ASM, and I forget the syntax, but I think we just do LGDT with I guess we call it address, and we need to pass it some number of things. Actually, statement found volatile, is it? Volatile. Sure. Okay, so expected that, found that. Okay. And I think I have an example of the syntax somewhere over here. So outputs and inputs, and name brackets the type and where it comes from, the actual variable. Okay, cool. Right, so I guess we should do something like address, we should just have it be some register, and it should come from self. Sure. Let's see if this builds, at least. It does. Well, that's huge news for us. Now, if we can go... Actually, yeah, it's not really huge news for us because we have not used this yet. So I guess we can go ahead and do const descriptors is import descriptors.seg, and we can do descriptors dot okay, well, hold on a second then. So let's do public function init takes nothing, returns void, and in this public function we are going to create const GDT. Oops, GDT is GDT dot create. Is that how we call this? Yes. And I guess we should pass it the VM, which would be vmem here. And this can fail, so this can fail. Just give me very nice. Yeah, it can fail. Cool. So now we do gdt dot load. And okay. I guess now we should go to main and do descriptors.init and pass it kernel vmem. Yeah, sure. And of course this needs to be tried. Okay. And I guess now we are going to have quite a few problems. Cool. So create is not public. Excuse me. Create is not public. No field or member create in GDT. Oh, of course. Of course. Let's do it this way. Okay, very nice. So 49, I think. This one I failed it. And 165. What's the problem here? Expected type info of type of whatever, and found phase mem range. Okay. So if I remove this, I guess I can simplify this. Yeah, there is no need to go through all of this. I can just do or else return error there. Right, we just need to get rid of this thing. So expect 3 arguments found 1 in 166. Allocate range takes 3 arguments. Oh, of course. So those are 2, and the third one is this. So descriptors 166 expected type pointer to vmem and found const vmem. Pointer to vmem and found const vmem, of course. So this one needs to go there and needs to go, oops, there. Found vmem. Right, so that's in main, and that should be something like that. Okay. And now everything we've broken in vmem itself. So vmem and 167. So mmap. Okay, so that's mmap. Mmap is not marked as public. That's fine. That's an easy fix. So 355. Expected type vert mem range found, a pointer to vert mem range. Okay. So this here is a pointer to, yeah, of course. Or is it though? What's the ranges list defined like? Self is self, and here T is any type, but this one here is defined as a list item, and list item has, well, no, it does have a vert mem range. Yeah, I don't see it. Oh, I think this is the problem. Yeah, this needs to go. So 357 expected type v address but found u64. Okay. Yeah, you're right. So const new start is int cast of rangeless start plus length, and of course this needs to rather it wants to become a u64. So I guess that, oh come on, right, fine. So u64, and I guess we could do this, and that should make it happy. And here we can just do start is so I guess we can just do cast I guess we can just set it as new start. That should be okay. So expect integer or vector found memory v address. Oh, it's not intcast, sorry, it's bitcast. And now that I think about that, I think this should also become a bitcast. Okay. So 371, and I guess this one is the same problem here. This needs to go, and this needs to yeah, sure, let's do the same thing. So new start is as u64 at bitcast of range.start plus length. Here, whoops, sure. and this one here becomes at bitcast of new start. Okay. So function with non-void arrow type implicitly returns. Nice. So 3, 4, 5. So this one needs to return a vert mem range. So we return here, we return here, we return in the else, but we never return outside of this. So I guess this would need to become unreachable. I guess that should fix it. Right, so now back to, rather still in vmem.zig, we have a pointer cast issue here. So expected pointer type, but found a mem range thingy. So are we trying to cast the start maybe? Yeah. Yep. Okay. Yes. Expected pointer type, but found U64. All right. Hold on. We have this start, and we'd like to have int from pointer. Pointer from int of whatever this is, and then we cast that pointer to, or rather, we can actually just do as, maybe this should suffice. So now back to descriptors 171. And I think this needs to become a bitcast. And still same here. Expected they pointed to descriptors of GD5, found a line 1 descriptors GD5. Yeah. So I guess the alignment is not really our biggest concern for now. So I can just remove this and have it be aligned however it sees fit. Okay, so return self. Okay, so I guess it really wants to. Wait, is this not the problem? We just want a pointer to self, actually. Yeah. It's still going to cry about the alignment. Alright, so let's just give it what it wants. I don't really care about the alignment for now. Expected type, so that's at 2, 4, 3. Okay, that's actually kind of really bad. Let me just try to think about this. Let's get rid of the alignment requirements. So here the bytes as value is FLCNOS. I think I should do an align cast. Oops. And I think I should also do something like this to make it happy. Yeah, I think it's a lot more happier about that. Actually, hold on. We have a problem here in mem.zeg type does not support field access. Oh, yeah, okay. So we need an actual slice. Allocated slice is allocated bytes. Actually, just thinking about this, is there any way we can just create our slice ourselves? Can we just do something like pointer is whatever that is, and I don't know, do length is vrange.length. Does not support struct initialization syntax. Okay. It was worth a try, I think. Right, so here we want to go from 0 to vrange.length. And here we want to have allocated slice instead. Same as here. It's not building. Undefined symbol address. And I think that's somewhere here. What do you mean? I think I know what it means. Unknown use of instruction without mnemonic. Very nice. Very nice. So let me just go back to CPU ID. And here we just did not have that issue. Can I go to something else like io.zeg? I guess we put the size specifier or size suffix here for all of these. Sure. You know what? Sure. Let's try. I don't know if this would work. Yeah, of course. Of course. Should we just do something like this? Yeah. Right, so let me try something else. Is it going to be happy with this? And it's happy with that. Magic. That's very nice. So the best way to see that the GDT has been set is to actually hook GDB to our kernel and see that it has been set. I'm not going to do that in this video, but let's run this and see that it works at least. Okay. And we have an exception for a page fault. Very nice. And is that in our kernel? I think it's in our kernel right after we so we do quick map and right after quick map, we get the exception. So let's go to our main. Oh, right, because we've just unmapped this value here. So if I do this, in theory, it should not crash anymore. Okay, well, it's not crashing anymore, but we are overriding an entry here, and that surely needs to be looked at. Yeah, but our kernel is running, it's not crashing, so everything we did so far has not crashed it. I guess that's good news. Well, that was pretty much it for this one. We made some great progress on GDT redefinition, and also we fixed some issues with our virtual memory management. So as we've seen, there are quite a few things that need to be corrected, and by corrected I mean redone, in our virtual memory manager, probably even the physical one, and we still need to work on our general purpose heap allocator. One thing I'm still debating here is for the changes we need to do in our memory management, should I actually make them on video, or are they so uninteresting that I should just blaze through them on off recording? So that's something I'm still debating. Actually, let me know your thoughts about that. If you've liked this video, leave a like. If not subscribed yet, please subscribe, and I'll see you next time. Fuck it out.